Hi, and welcome to this quick review of the Arrhenius equation. So for this to be a quick review, it's not intended to teach the mathematics behind the Arrhenius equation from the beginning or do any worked examples. It's better considered as a review of the process of using the Arrhenius equation and how it fits into other A-level ideas about reaction kinetics. So basically, reaction kinetics is the extension of the collision theory you would have learned at GCSE, and is introduced at A-level via the Boltzmann distribution. So the activation energy, or EA, is the minimum energy required to start a reaction by breaking bonds. And the animation on the left is an enthalpy profile diagram of an exothermic reaction. It also shows what happens when you add a catalyst. This relationship can also be represented via the Boltzmann distribution. So the Boltzmann diagram at the bottom of the page shows the relationship between the normal activation energy for an uncatalyzed reaction and the activation energy when a catalyst is present. The green shaded area represents the molecules that can that have energy at or above activation energy for the uncatalyzed reaction. So the pink shaded area now represents the additional proportion of molecules that can react now due to possessing energy greater than or equal to the activation energy for the catalyzed route. So how does this all fit into the Arrhenius equation? So within the Arrhenius expression, the expression in the black box on the left represents the shaded region in green in the Boltzmann diagram below. So that therefore the proportion of molecules with kinetic energy greater than activation energy. So within the Arrhenius equation, capital letter A stands for the frequency factor, or the number of these particular molecules or particles that also are able to collide with the correct orientation and therefore will react. Not just have enough energy to do so, but once they've collided, they will collide successfully with the activation energy required and in the correct orientation. So let's have a quick look at why we use the Arrhenius equation in the first place. If we take a random rate equation such as the one on the screen, if you happen to plot K against temperature, you'd actually get a curve. And the problem with curves is they don't have a regular gradient. So the fact that they don't have a fixed gradient can make curves a bit difficult to work with mathematically. So what we do is we use a logarithmic version of the Arrhenius equation to straighten this curve out. So we can plot the natural log of k against 1 over t and get a straight line of negative gradient if we're provided with the data. So the point at which the line crosses the y-axis, provided at this point x is also 0, is called the y-intercept. It also gives us the natural log of a. Now you may notice that the gradient is actually minus Ea over r, which is provided in your data sheet as the gas constant, and it has that particular value. So if we now have the gradient as minus Ea over r, we can actually work out what the activation energy actually is in joules per mole. So technically, what they might ask you to do is work out the activation energy by doing an Arrhenius plot of a set of data that they'll give you. So let's look at what this might look like. So the data you'd be given would be on the left-hand side, K versus T. And all you'd have to do would be to do natural log of K in each case. And the natural log key is in the top right-hand corner of the calculator display. I'll just highlight it for you. And at the same time, you can change T into 1 over T. Now you're ready to do your plot. So because you'll find that most natural log k values will tend to be negative, you'll need to plot a graph axes in this manner. So 1 over t can be the x-axis and natural log of k, or ln k, can be the y-axis. So if you're lucky with your data that you're provided with, you should end up with a nice straight line like that, and you can do a line of best fit, which should allow you to work out what the natural log of a is in the Arrhenius equation. However, what if it doesn't work out like that? What if we don't actually have a line that allows us to do an intercept? So if you remember, the Arrhenius plot can only work if the y-intercept is at x equals 0. So the diagram on the left will only actually hold true and give you a correct version of ln A if x happens to be 0. So let's have a look at an alternative situation where the data set might not provide that kind of plot. So in this case you can see it's a little bit less easy because the y-axis isn't bisected in the same place as the y-axis in the red version. So what you need to do here is a little bit of extra maths. It's not difficult, it's just an extra stage. You need to work out dy over dx. So in this case, remembering what the gradient represents in the Arrhenius equation, we can substitute in the value for dy over dx as minus Ea over r. If we take natural logs throughout the Arrhenius equation, it turns it into ln k equals minus Ea over r times 1 over t plus ln of A, which quite happily equates to y equals mx plus c, which is essentially the way of representing a straight line, which is why we straightened the curve in the first place, as like we discussed earlier in the clip. So now we have everything that we need. So EA can be calculated using dy over dx. R is given from the data sheet. So therefore the natural log of A can be found by substitution. So irrespective of what kind of plot you actually end up with from the data, you can either find ln A from direct bisection of the y-axis at x equals 0, or you can calculate it by working out the gradient of the axis and substituting in the values. Okay, so like I said, this was meant to be a quick review. Hopefully you find it fairly useful. There are lots of good videos out there on Arrhenius. I've done another one on my channel, which is about 45 minutes long. It goes into the maths a lot more and does some worked examples for you as well. But hopefully this is taking you through some of the major parts of the process and the ideas behind it. So thanks for your time and see you soon.